Okay, so thank you everyone for the invitation. So I'll be talking about, as Ala said, global rigidity of transversely holomorphic Anosov flows. So we'll be discussing each word, what it means, progressively, because transversely holomorphic, I don't know if everyone knows what it means, but we have to get to some foundations about foliations, etc., in order to really understand that concept, which is not difficult. So I'll be first exposing the context about around this research and talking about the history behind it. After that, I'm going to talk about basic stuff, basic definitions of foliations. So a foliation, what is holonomy? I'll be talking about this is not how do you say that? I'll be talking about weak foliations. Weak foliation is just when you have a foliation which is invariant by our flow that you work on. Then you can define a weak foliation. It's how I call it, but it's universal. Like in Anosov flows, we have the weak stable and weak unstable foliations. But I call weak foliations because I've also worked on partially hyperbolic Anosov flows which are transversely holomorphic, and I needed this definition which I didn't found on the internet or so I will be talking also about weak foliation, but just like one or two slides, but I have to put it there. Then we'll be able to define transverse holomorphy for a foliation, and I will be giving the basic two examples of transversely holomorphic flows in dimension 5 in particular, but one example can be defined in any dimension, in any odd dimension. And after that, I'll be talking about Anosov flows, transversely holomorphic Anosov flows. So I'll be giving the definition and I'll be going into all the results that I have in my case, in the continuous case. So I'll be showing that strong leaves are complex. Then the weak foliation, the weak stable and weak unstable foliations are transversely holomorphic. Then each strong leaf is complex affine, and then the weak foliation are transversely projective with respect to these affine structures, and this will lead to the classification of transversely holomorphic Anosov flows with the help of the developing map for GX structures defined by Thurston. So the main tool during this of this article is that of a foliation. Basically, it's a partition of a manifold into immersed submanifolds of the same dimension, which look like the horizontal foliation. So this is your partition of the manifold into leaves. And locally, these leaves are sent to the horizontal lines of open subset of R to the n if your manifold has a dimension of n. And the main subject is that of a transversely holomorphic flow. So transversely holomorphic for a flow, basically what it means, you have a smooth flow, and this flow, as we'll see, will be inducing a foliation by orbits. And this foliation's holonomy is given by holomorphic maps. Holonomy, what it means is that if you have 2 points x and phi t of x which are in the same orbit, and you define two transversal at these 2 points, so a transversal is a smooth embedded submanifold which is transverse to the flow direction, to the vector field direction, then you can define, for example, if you have a point z here in the transversal t, you can define for this point z another point which lies in this transversal t phi t of x, which also belongs to the same local orbit of z. And this is the holonomy. The holonomy, basically what it means, you take this point and you send it here. And a transversely holomorphic flow is a flow such that if you do this operation on any points on the same orbit and with respect to any transversals, then this map is holomorphic. So such a flow can only exist on odd dimensional manifolds because the orbit foliation is of dimension 1 and the transverse dimension must be even. So it can only exist on dimension 3, 5, 7, etc. And precisely, it has been classified in dimension 3 like 30 years ago. I'll be talking about that, but just first, I'll be in this recap. I'll be saying a lot totally geodesic, umbilical, and Riemannian. So I just explain what that means. Totally geodesic means when you have a foliation which is totally geodesic in the sense of HNGs and Marco Brunella, is that the second fundamental form of each leaf of this foliation is identically equal to 0. Umbilical, it means that each leaf is such that the second fundamental form is a multiple of the induced Riemannian metric on that leaf. And a Riemannian flow or a Riemannian foliation is a foliation such that the holonomy is given by not holomorphic maps as we said in our case, but is given by orientation preserving isometries. Okay. So the classification results are that of HNGs first in 1982. He classified totally geodesible or totally geodesic foliations of codimension 1, and one can show that these foliations are equivalent to the data of a Riemannian flow, which is transverse to a codimension 1 foliation. 2 years later, Yves Carrière classified in dimension 3 Riemannian flows. So it's like he classified transversely orientation preserving flows. Okay, he classified, if you want, transversely rotation flows. The holonomy of Riemannian's flow is precisely that which is given by rotation, because an orientation preserving isometry of C is precisely a rotation. So this gives first set of examples of transversely holomorphic flows in 1984 by Yves Carrière. 10 years later,
But
Marco Brunella and
there are the translation or
oh
uh,
yes, sorry, also the translation, sorry, yes, and the rotations, yes. So 10 years later, Marc Brunella and Ecengis classified umbilical foliation. So as we said, an umbilical foliation is one such that the second fundamental form of each leaf is a multiple of the Riemannian metric, the induced Riemannian metric. And one can prove that because in dimension 3 holomorphicity is equivalent to conformity, then these foliations are equivalent to transversely holomorphic flows, which are transverse to a codimension 1 foliation. So this is quite restrictive. And 1 year later, Brunel-Aegis, what they did is that they classified transversely holomorphic flows in dimension 3. Okay, so this is, if you want, to my knowledge, how we get to transversely holomorphic flows. First, totally geodesible foliation, then Riemannian flows, which are particular examples, then umbilical foliations, and then transversely holomorphic flows. But these only exist, these classifications work only in the dimension 3, and in particular in Brunella and Gis' classification, it relies heavily on the fact that in this little dimension, then holomorphicity is equivalent to conformity, etc., which is what I'm going to talk right now. I'm just going to detail a little bit what Brunella and Gis did in their 1996 classification, 1996 classification, and also 1995. So in the general case, so in 1996, they erased this assumption of being transverse to a codimensional foliation. So they only work with transversely holomorphic flows. And what Brunella did first is that he uses, instead of a codimension one foliation, which is transverse to your transversely holomorphic flow, he uses a transverse type disk field, which allows him to define an elliptic operator, then a harmonic atlas, and under some condition, he complexifies the orbit foliation of the transversely holomorphic flow. So he gets a holomorphic foliation on a compact complex surface. And these, using the Enriquez-Kodaira classification, then he concludes. And on the other hand, GIS removes this rationality condition. I'm not going to talk about it. It's about the harmonic atlas. But he manages to remove this condition, and he proves that your transversely holomorphic flow is necessarily Riemannian. And as we said in 1984, Riemannian flows in dimension 3 are classified by Yves Carrière. So they come to their conclusion. And as I said, both methods rely on the fact that the transverse complex dimension in dimension 3 is 1. So conformity is equivalent to holomorphy. Harmonicity is equivalent to holomorphy in the sense that if you are a harmonic function, harmonic functions are precisely a real part of holomorphic functions. And this dimension also uses the Enriquez-Kodaira classification of compact complex surfaces, and all that is a priori not generalizable to higher dimensions. Also, I wanted to talk another fundamental article for me in order to come to my conclusion, is that of Etienne in dimension 4. He classified holomorphic Anosov diffeomorphisms on compact complex surfaces. So this is the discrete hyperbolic case, and you'll see that all of my results are just, if you want, um, uh, are uh, are totally similar to his results, because I just noticed that if you are in dimension 5 but in the continuous time case, then you can extrapolate his results in order to come to the conclusion. However, there will be a little twist, um, because at the end he proves that the only possibility is when you have a holomorphic Anosov diffeomorphism on a compact complex surface. He proves that the only possibility is that of a automorphism of a complex torus. Okay, and we're going to prove that in our case in dimension 5 there is, if you want, the automorphism of a complex torus case. It's not it's will have the suspension of an automorphism of a complex torus. But the second possibility is that we'll see is that of the geodesic flow on a hyperbolic 3 manifold. Blah blah blah. Well, after that, Gis extended these ideas to the holomorphic Anosov flow case, so in dimension 6. And our approach is, as I said, to generalize Gis's techniques to transversely holomorphic flows that are Anosov. And one big difficulty will be that of Markov partitions, because Markov partitions, if I want to apply um, his method in order to prove the transverse complex projective structures of the weak foliations, the weak stable and weak unstable foliations, then I'll have to ask another mathematician, which is called Ratner, which proved the existence of Markov partitions for Anosov flows, transitive Anosov flows of arbitrarily small sizes. Ok. So, okay, so about foliation. So CR foliation, a regular foliation, is given by, on a smooth manifold, is given by a maximal atlas, CR atlas, whose change of charge are of this form. So the second component depends only on the second component, so on y. Okay, but it can also be given by a partition of M into immersed manifold, which locally look like the horizontal foliations. And I insist on the fact that the foliation is 0R. In this case, R is greater or equal than 1. Data exclusion, je voulais dire. Yes, well, I insist this definition is available only for, not only, but for R greater or equal to 1. And we'll see that in the in dynamical studies, the foliation that one can encounter are mostly only continuous. For example, the strong stable and strong unstable foliations of Anosov flow or diffeomorphism are only continuous, well, older continuous. So this is not immediate. For example, flows are give rise to smooth foliations. If you have a non-vanishing smooth vector field, then it generates a smooth flow whose orbit form a one-dimensional smooth foliation. So this is just the picture. Locally, the change of charge diffeomorphism map horizontal lines to horizontal lines. So this is just the foliation charts. So as I said, we have to define foliation with CR leaves in the sense that it's weaker than a CR foliation because, as I said, one encounter often foliation which are only continuous or continuous but with CR leaves, and the definition is quite similar. So if we only except that we only use a continuous atlas, not a CR atlas, but whose change of charge are of the same form, and we want that this map là Fij, its restriction, this map with respect to x is CR. So if you want just the for y fixed, this map is if you want a change of chart diffeomorphism for a fixed leaf. Okay, so this is why we say a foliation with CR leaves. And in the equivalent definition, we use a continuous chart such that the foliation look like the horizontal foliation, and the restriction of that chart psi to each leaf is CR. And we'll say that a foliation has uniformly CR leaves if this map Fijxy is CR and its partial derivatives of order k smaller or equal to r are depend continuously on x and y. And we'll call continuous foliations with uniformly C1 leaves. And for example, the strong stable and unstable foliation of an Anosov flow or an Anosov diffeomorphism are foliations with uniformly C infinity leaves, and this we'll need it in order to also come to our classification. Okay, and now we can define holonomy. So basically, holonomy, you have a foliation CR where R can be equal to 0. And you take x and y 2 points on the same leaf, and you take alpha a path from x to y in L. You take small transversal T and S, and the holonomy is a germ of diffeomorphism from T to S. I'm going to show the picture, it's easier, which basically assigns, as I said earlier, Z2. So if you have x here, y here in the same leaf of F, you have here in alpha, in purple, your path alpha. Then locally, if you want, what you do is that you take your transversal T here and your transversal S here at Y and at X. So you take a point Z in T and you intersect first. Well, the definition first is local, okay? So you first have to define holonomy locally. So you take 2 points which are close enough, and you get that from Z, you draw the local leaf of Z and then it intersects at S. It intersects S at a unique point, which is the holonomy. So basically, you move from here to here. So this is the case when two points are close enough, and where they are not close enough, you have to divide your path into smaller path. When, for example, here x and x1 are close enough, so you define the holonomy between these 2 points, then these 2 points, etc., and you get the global local holonomy. If you it is just the definition of holonomy. You take two transversal at x and y, and you intersect the leaf of some point z in T with the transversal S at Y. And this is the holonomy. The bridge to smoothness. Um, Usually, when, in my case, when I study dynamics, as I said, often the foliations I encounter are only continuous, but we're able to upgrade the regularity thanks to Journé's lemma, as I'll be talking about it in like 2 minutes. And Journé's lemma basically says that if you have a foliation with uniformly smooth leaves and uniformly smooth holonomy, then your foliation is C infinity, even though initially it's only continuous. So we have to define what is uniformly to have uniformly smooth holonomy. Foliation, this definition, I did not find it in any article. I defined it myself because, I found it in 2 or 3 articles which are not adequate to my, um, which are not perfectly adequate to my case, but it's the same idea. We say that a foliation has uniformly smooth holonomy if locally there exists a transverse foliation T with uniformly smooth leaves, which is transverse to the initial foliation F, as such that for every x, the holonomy of F with respect to leaves of T, which is the local foliation transverse to F, this holonomy is C infinity. So the partial derivatives of any order of this map exist, but also these derivatives vary continuously with x and y. Okay. And Journé's lemma says that if you have such a foliation which is moreover with uniformly smooth leaves, as we have defined earlier, then your foliation is C infinity. And this is quite strong because you only assume your foliation is continuous, and if you want, if you restrict it to leaves and to the transverse direction, if you say that both are smooth, then your foliation is smooth. So as I said, when you have a complete smooth flow and F an invariant continuous foliation, then you can define transverse to the flow direction. Then you can define a weak foliation, as is the case with Anosov flows. And I needed that a lot also in the partially hyperbolic case in order to extrapolate the results of the discrete cases. Because, for example, as I said, these results, I extrapolated the results of HNGs in the discrete case, and I needed the fact that we can define a weak foliation, but this is also true in the discrete partial hyperbolic case. I've also managed, I think, some extrapolation from the discrete to the continuous time case, thanks to this little trivial, not trivial, but not difficult lemma, which says that you can define a weak foliation that integrates the sum of the vector field x and the tangent bundle of your given foliation f, which is invariant and transverse to the flow direction. And this is just a picture of how we defined it. So locally you have in green the leaves of f, and using a flow box you can have your flow in gray, which is given by the horizontal vector field. And then you can define the weak leaves as the union of all these green leaves because the F by assumption is invariant by the flow. And here also, it's just a picture in order to illustrate this. So now we can define transversely holomorphic foliations. Foliation is transversely holomorphic, basically, if it can be defined by a foliated atlas whose transition maps are holomorphic. So the Hij, if you remember correctly, are the second component of the chart diffeomorphisms. And we can characterize such foliation in the following way. The fact that your given foliation is transversely holomorphic is equivalent to the fact that holonomy maps between any transversal are holomorphic. And when R, because this definition and this characterization is also true where R equals 0, and when R is greater or equal to 1, then we can prove that it is equivalent to the existence of an almost complex structure on the normal bundle to the foliation. As we said, a transversely holomorphic foliation, the transverse direction is even dimensional, if I would say. So the existence of an almost complex structure whose induced almost complex structure on any transversal is integrable and invariant under holonomy. Basically, the idea is that the definition is equivalent to the first point because, in fact, the Hij in the definition are the expression of holonomy maps in appropriate coordinates. The fact that the definition implies the second point, that is the existence of an almost complex structure, comes from the fact that the transition function of the normal bundle are given by the different differentials of the transition map. So we can define locally the almost complex structure and then extend it globally. And the fact that 2 implies 1 is straightforward not by definition, but because if you have an almost complex structure on the normal bundle, then you can define it on any transversal to the foliation, and by definition, this complex structure is integrable and invariant under holonomy. So you get that holonomy maps between transversal are holomorphic in certain coordinates. Okay. What I'm going to use frequently is that if two foliations are transverse G, F and G has complex sleeves, and the holonomy of F with respect to G leaves is holomorphic, then by analytic properties of holomorphic maps, F has uniformly smooth holonomy. This happens frequently in the Anosov case, but also in the partial hyperbolic case. And in particular, if F has uniformly smooth leaves, then by Journé's lemma and the previous characterization, then F is smooth transversely holomorphic. So you start with F, which is just continuous and whose holonomy with respect to G leaves, where G is a transverse foliation to F. And the holonomy of F with respect to G leaves is holomorphic. Then you end with F being smooth transversely holomorphic. And this is what we're going to do a lot, is that we start with a continuous foliation, and thanks to holomorphicity, we upgrade the regularity until, well, in this case, for the Anosov case, until reaching the classification. The idea of proof, yes, as I said, holonomy maps are uniformly smooth because they are holomorphic, basically. And Journé's lemma and the characterization give the fact that the foliation is smooth and transversely holomorphic. The two basic examples, excuse me, just 30 seconds, I have to put the charger on my laptop. So the two basic examples of transversely holomorphic flows are that of the suspension of a holomorphic diffeomorphism. So it's like the analog of the discrete case. If you have a holomorphic diffeomorphism, then you can define a transversely holomorphic flow in the following way. So you start with a holomorphic diffeomorphism on a compact complex manifold. And then Z acts freely and properly discontinuously in the following way. Okay, and so it defines a smooth manifold with a smooth foliation, which is the foliation, the image of the foliation. For example, a leaf is a point times r. Okay, so you get a smooth foliation, which is induced by a flow whose action in the is the following. You just well, phi t of x and s is just x s plus t in the following way. So you start with your complex manifold F and your diffeomorphism F, no, X, F of X, F2 of X, and you define this cylinder where you identify this point x1 with F of X, and you identify F of X 1 with F2 of X, etc., etc. So the suspension flow is this one. So it's an orbit is given like this, and then we go on, etc., etc., etc. So this is a generalization of not a generalization, but a construction from discrete to continuous time case. And the other example, which is really uh, uh, specific to the continuous time case, is that of the geodesic, so the geodesic flow of the hyperbolic three space. So if we use, because it's why I prefer the upper half space model H3 with the Poincaré metric, then the geodesics are vertical lines and semicircles orthogonal to not to the boundary at affinity, but the well the z equals zero plane. So the geodesic are these. So we can identify the set of oriented non-parametrized geodesics with P1 times P1 of C times P1 of C minus delta. Delta is the diagonal of P1. So P1 of C, it's of P1 of C times P1 of C. It's just the points XX where X lies in P1 of C. Because I can just show the picture here. So this is H3. So this is the I don't know how to say the well the base of H3. And geodesics are exactly vertical lines like this, and semicircles which are orthogonal to the base, to C. So for any of these geodesics, you can define two endpoints. So for example, for the vertical lines, the endpoints are infinity and some point here. And for a semicircle is the two endpoints are 2 points in the base, which are in any case different. So this is why I said that we can identify the set of such geodesics with this set, because C union infinity is just the sphere, the complex projective space of dimension 1. So therefore, there exists a submersion which goes from the unit tangent bundle of H3 to P1 times P1 minus delta, whose fibers are exactly the orbits of the geodesic flow. Basically, you start with a unit vector tangent to H3, then you define the geodesic associated. You have two endpoints. Well, you say that the image of D is these two endpoints, and they are different because they're different. Okay, and this gives a transversely holomorphic flow on H3 because the geodesic flow can be defined by this submersion into a complex a complex manifold. So this is the case in the hyperbolic three space, but it's not compact. But the compact case is not much difficult because compact hyperbolic three manifold is the quotient of H3 by a subgroup G of PSL2 of C, which is discrete, torsion free, and co-compact. Okay. And so because because the geodesic flow on H3 is transversely holomorphic, then the one on V, which is the quotient space H3 with J, is also transversely holomorphic. And then we get to the definition of we get to the definition of Anosov flows, which is just a smooth flow which is generated by a nowhere vanishing vector field such that the tangent bundle of M can be decomposed into three directions, the vector field X inducing the flow and two subbundles ES and ES and EU. ES consists of the vectors which are uniformly contracted under the action of the flow, where the action is forward in time, and EU is the set of vectors which are uniformly expanded. They are called so ES the strong stable and EU the strong unstable bundle. And a fundamental result is that they are integrable to continuous foliation or Holder foliation, sorry, with uniformly smooth leaves, which are going to be denoted by FS and FU. And as we said, we can define, because these foliations are invariant by the action of the flow, we can define the weak stable and weak unstable foliations, which are also continuous foliation with uniformly smooth leaves. I precise that they are foliations with uniformly smooth leaves because, as we said, using Journé's lemma, we're going to improve the regularity of such foliations because initially they're only continuous. So the two fundamental examples in dimension 5 are that of a suspension, the suspension flow of an Anosov diffeomorphism on a compact 4 manifold, and the geodesic flow on the unit tangent bundle of a compact hyperbolic 3 manifold. And what we're going to prove is that under the assumption of transverse holomorphy, these two examples are the only one. Okay, so the only transitive Anosov flows which are transversely holomorphic in dimension 5 are the suspension of a automorphism of a complex torus and the geodesic flow of a compact hyperbolic space after finite covering. So from now on, I'll be talking about some of my results. So the first step, when you have a transversely holomorphic flow, transversely holomorphic Anosov flow, but it's also the case for a transversely holomorphic partially hyperbolic flow, which I'm not talking about here, is that the strong stable and strong unstable leaves are complex manifolds, and this come from the fact that well, the flow is by definition transversely holomorphic. So because the strong stable and strong unstable leaves are transverse to the flow direction, so they get some of the complex transverse structure, if you want. And the flow maps act also holomorphically between such leaves. The idea is the following, as I said. If you remember correctly, when you have a transversely holomorphic foliation, then it can be defined by here, because the flow is smooth, it can be defined by a smooth almost complex structure on the normal bundle to the foliation to the flow. Okay. However, we cannot say that there exists a smooth almost complex structure on ES time plus plus EU because it's only continuous, so we can only define a continuous almost complex structure on this. And by definition, by the characterization, it is invariant under the differential of the flow maps. And because of the characterization of the strong distribution, the characterization is just the fact that these two inequalities, they characterize the strong, stable and unstable distributions. So because of that, that continuous almost complex structure can be restricted onto ES and EU as a smooth, integrable, almost complex structure, which is invariant between by the action of the flow. So this is how we get that the strong, stable, and unstable leaves are immersed complex manifolds. Now that we say now that we know that the strong, stable, and strong, unstable leaves are holomorphic, we can prove that the corresponding weak foliation is transversely holomorphic. So, for example, if you have a transversely holomorphic Anosov flow, and also we have to assume that the complex dimension of, for example, EU is 1, then we are going to prove that the weak stable foliation F WS is C infinity, so it's smooth and transversely holomorphic. I insist initially such a foliation is only continuous. So because we assume our flow is transversely holomorphic and the complex dimension of its transverse structure is 1, complex dimension is 1, then we'll get the fact that the weak stable foliation is smooth and transversely holomorphic. And it uses the fact that, as I said, this idea was initiated by Etengis in the discrete case. He proved that the stable foliation is holomorphic because in a holomorphic manifold, transversely holomorphic foliation, well, in a small dimension, is holomorphic. And he uses the fact that 2 points on the same stable leaf are contracted under they approach each other under the action of the flow. Okay, in our case, it doesn't work the same way because the weak stable foliation does not consist of points that are contracted under the action of the flow because there exists the flow direction. But we have proven in the previous proposition that the flow acts holomorphically between strong stable or strong unstable leaves. So what I'm going to say is that in order to prove that, I'm going to show a picture in order to demonstrate this point, but we compute the holonomy of the weak stable foliation with respect to unstable leaves. That's obvious. I'm going to show the picture in order to explain that. So you have Z here. No, sorry, you have X here and Y here, which are 2 points on the same weak stable leaf. So as we said, the weak stable leaf consists of, if you want, the union of the orbits of points which are in the strong leaf of X. So your point Y you can project in order to have another point Y prime, which belongs to the strong stable leaf of X. And in order to prove that the holonomy between X and Y is holomorphic, then you will remark that this map can be decomposed into the composition of the holonomy between X and Y prime and the holonomy between Y prime and Y. But the holonomy between Y prime and Y is just because of the fact that the involved foliations are invariant under the action of the flow. This holonomy is just, for example, is Y prime is here and Y is phi t of Y prime for some t, then this holonomy between here and here is just phi t. Okay, and in the previous proposition, we said that this map between strong unstable leaves is holomorphic. So we know that this part, if you want, is holomorphic. So we only have to prove that if you have 2 points on the same strong stable leaf, then the holonomy between strong unstable leaves is holomorphic in order to conclude to the fact that the weak stable foliation is holomorphic. And this is just, as I said, an extrapolation. Now that we have done this little trick, an extrapolation of Gis's idea in the discrete time case, we approximate uniformly the holonomy by a sequence of quasi-conformal maps, because what we're going to use is that since the strong unstable distribution is of complex dimension 1, then holomorphicity is equivalent to conformity. So we only have to prove that the weak stable foliation, the weak stable holonomy is conformal, and we're going to approximate this very holonomy by a sequence of quasi-conformal maps whose constant is bounded by 1 plus epsilon for any epsilon, and we tend epsilon to we make epsilon go to 0. And this is how we get the fact that the weak stable holonomy uh, is 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 conformal, thus holomorphic. Okay, well, I don't know if I have enough time, so I'm going to skip over some things. So this is just a definition of a JX manifold. It's a generalization of smooth manifold. It's a manifold. Now we're going to define complex affine manifolds, for example. So it's just a manifold which can be defined by a maximal atlas of charts, whose images are in some manifold X, okay, and whose transition maps are restrictions of elements of some group G. So as I said, if X is just C and G is the group of affine automorphism, complex affine automorphism of C, then we get a complex affine manifold, and we can define in the same way a transverse GX structure for a foliation by imposing the fact that the transition maps are restrictions of element of J. Okay, well, this is just the same formulation, but I had to put it there. And for example, yes, if you X is the complex projective space of dimension 1, as and G is the group of automorphisms of X, so they are the Mobius transformations, then F is said to be transversely complex projective. What Thurston did many years ago is that he defined the what we call a developing map when you have a foliation with a transverse GX structure. It's a, if you want, it's a submersion, a global smooth submersion from the universal covering of M to X, the manifold encoding the transverse structure. Okay, together with a homomorphism, a group homomorphism, H from P1 of M to J, such that the lifted foliation on the universal covering space is defined by D, so the global submersion. So basically, you start from a foliation with a transverse JX structure, you lift it to the universal covering space, and you get a foliation, which is the lifted foliation of F, and it is defined by this submersion. Okay, and you have this relation between the developing map D and H, the holonomy homomorphism. Okay. And the characterization of such foliation is analog to that of a transversely holomorphic foliation. Uh, you only have to check that the holonomy maps between transversals is a restriction of an element of J in order to prove that the foliation admits a transverse JX structure. So here we're going to prove after that the weak stable and weak unstable foliations are transversely complex projective, and that using the developing map of Thurston will lead to the classification of such flows. So the first step is to prove that for a transversely holomorphic Anosov flow, is that the strong unstable and strong stable leaves are complex affine, and the flow acts affinely between such leaves. Okay, if the complex dimension is 1. This is why we get some classification result when the dimension of the manifold is 5. Is because all the strong unstable and the strong stable foliations will be of complex dimension 1. And the core idea how we get these complex affine structures on the strong and stable leaves comes from Giss's idea again. He links complex affine structures on a holomorphic curve with equivariant sections sigma from L1 to L2. L1 is the set of one jet of holomorphic curves, and L2 the set of holomorphic two jets of holomorphic curves. I don't think I have time in order to talk about this. So basically, the fundamental lemma is that there is a correspondence between, as I said, complex affine structures on holomorphic curves and holomorphic sections of L2 to L1, which satisfy this condition, which he calls equivariance condition. Okay. Um, Okay. So the link comes from the fact that if you have a complex affine structure, then you can define an equivalent section of L2 to L1. So I repeat, L2 is the set, as I said here, is the set of R jets. LR is the set of R jets of holomorphic diffeomorphisms between open sets of zero and open sets in L. It's just it's a jet bundle if you want. So if you have a complex affine structure, you can define such a section, which is also equivariant locally by this, because L2 can locally is trivialized by some function, and locally you can define sigma in the following way. And this gives a section globally because of the fact that initially your holomorphic curve is complex affine. And conversely, you can define, if you have such a section, that is such a section, a holomorphic section satisfying blah blah blah, this equivariance condition, then you can define locally a holomorphic or ordinary differential equation whose solutions give you the affine charts of the holomorphic of the complex affine, the affine chart, yes, for the holomorphic curve. And we can do the same, not for a holomorphic curve, but with a continuous foliation with holomorphic curves, with holomorphic leaves of the complex dimension one. So in order to prove that there exist complex affine structures on the strong unstable leaf when the strong unstable distribution is of complex dimension one, we have to prove that there exists a continuous section of M2 to M1, where MR is the set of R jets of holomorphic diffeomorphisms between open sets of zero onto open sets in leaves of your given foliation with holomorphic leaves F. You have to find such a section whose restriction to each leaf, to each strong unstable leaf is holomorphic, and also which satisfies this equivariance condition. And also in the theorem, we want the flow, our transversely holomorphic flow, to act affinely between strong and stable leaves. And this means that if you want the induced flow map commutes with this very section sigma, the induced flow map in the space of jets of diffeomorphism. Uh, yeah, the idea is just a fixed point theorem because the flow acts as a contraction, well, as an expansion between strong unstable leaves. So it's just a fixed point theorem, and we use the fact that the section we get its restriction to each strong unstable leaf is holomorphic because the uniform limit of a sequence of holomorphic maps is holomorphic. I have to skip over that. Okay. And yes, so now that we have for a transversely holomorphic Anosov flow, complex affine structures on the strong unstable leaves. Again, if we assume the complex dimension to be of the strong unstable distribution to be 1. Then we're going to prove that the weak stable foliation, so it's the transverse foliation associated to the strong unstable one. Then we're going to prove that this foliation is smooth transversely affine. No, transversely projective. Transversely affine will correspond to the suspension case. Suspension case. Excuse me. Yes, the added assumption is that here I think we have to assume the flow to be transitive. That's not the case in the discrete setting. I don't know if we must assume this, assume that the flow is transitive, but in order to use Ratner's article, then I have to assume the flow is transitive. Basically, it's um, to get Markov partitions of arbitrarily small size. This is just a reminder of the Schwarzian derivative, which encodes the fact that the holomorphic diffeomorphism between one projective manifold is projective. It's encoded in this form, in this quadratic form. So this is just some properties satisfied by the Schwarzian derivative. So our
Mounib,
goal is to prove that the weak stable holonomy between local unstable leaves is projective. So as we said, it's encoded by the Schwarzian derivative. So we have to prove that the Schwarzian derivative of the holonomy of the weak stable leaf between strong unstable leaves is equal to 0. So we define, as Gis did, a quadratic form on the strong unstable bundle of X. Yes, as the Schwarzian derivative of h at x, and the goal is to prove that this derivative, this quadratic form, sorry, is identically equal to 0. So we use, as I said, Ratner's the theorem, which states that a transitive Anosov flow on a compact manifold admits Markov partitions by parallelepipeds of arbitrarily small size. So we're going to define what is a parallelepiped. Basically, it uses the local product structure between the weak stable foliation and the strong unstable foliation in the following way. I'm just going to show the picture. So if you have some point x0 here, and you draw here in green, it's local strong stable leaf, and here in red, it's a local strong unstable leaf. If you have 2 points here, y here and z here, then you can define some point here x, which is the intersection between the local strong unstable leaf of y with the local weak stable leaf of z, because the weak stable and the strong unstable foliations are transverse, and the yes, and that's it. And because we're in a compact manifold, we can define this for a fixed delta. Okay, so what I wanted to say is that how do we say that? Okay, a parallelepiped is just first, in order to understand parallelepipeds, we have to understand parallelogram. Parallelogram. So a parallelogram is just, if you want, the image of two we call admissible subsets of the strong local stable leaf of x0 and the strong unstable leaf of x0 under the local product map. Okay, so a parallelogram, if you want, is just well, I think we can find, yeah. Well, it's difficult to see, but it's just, if you want, like this. P is a parallelogram, is the image of C and D for some point x0 here. Okay, under the local product structure map. Okay, the Bowen, I don't know, Bowen bracket, I don't know how we call it, but you have some point x0 here. You can draw its strong stable leaf, and here you can draw its strong unstable leaf. Then Ratner proved that you can find finitely many points and some subsets C and D, such that when you compute all the Bowen brackets between these 2 points, you get, well, a parallelogram here in vert khaki. And a parallelepiped is just this parallelogram which we extend by the action of the flow. Okay, so you come from you start here with the parallelogram, and you go to another parallelogram, and the whole gives you a parallelepiped. Well, it's quite. This is, if you want, this is the mainly, I think, for to my understanding and how I struggled with all that. This is the part where you step up from the discrete case of HNGs to the continuous case. It's not. I think it's not obvious. Um,
So,
well,
so sorry for interrupting.
yes.
So just the time is very limited.
Yes.
Maybe
Sorry.
you can go to the classification.
Okay. Okay. So basically, okay. Well, we prove the fact that the holonomy is projective by proving that Q is equal to 0, by proving that this map is equal to 0, and using some topological properties in C, we prove that there is a contradiction, and so the weak stable foliation is complex projective. So the flow is immediately transversely this PSL2 times PSL2, P1 times P1. Okay, and so we can come to the classification. So using the developing map, as I said, of Thurston, there exists the developing map for the weak unstable foliation and the weak stable foliation. So it gives a map, developing map for the flow, etc., etc. Well, I don't have time to develop all that, so I'm just going to say that the pre-classification result is that for a transitive, transversely holomorphic five-dimensional flow, when you lift your flow to the universal covering space, then the orbits are exactly the fibers of D. D is this, okay, and D1 corresponds to the transverse projective structure of the weak unstable foliation, and D2 to the weak stable foliation. And you get that the image of D is of two forms. The first is this one, and the second, this one. The first form will correspond to the suspension case, and the second to the geodesic flow case. Well, this is the idea, so we prove that by induction. So in the first case, briefly, how do we come to the suspension case? If the image of D um, is well, what is C times C, then we prove by the properties of D and H that H takes value in affine, the group of affine automorphisms of C times affine automorphisms of C. And therefore, the weak unstable the weak I said unstable. Well, the weak stable foliation, but it's the same, is transversely affine. By a result of Joseph Plante, the flow is orbitally equivalent to the suspension of an Anosov diffeomorphism. And in our case, since the flow is transversely holomorphic, we prove that the Anosov diffeomorphism is in fact a holomorphic automorphism of a compact complex surface, and thanks to the classification of GIS in the discrete case, we have that this diffeomorphism is in fact a hyperbolic automorphism of a complex torus. And so in the first case, our flow is equivalent to the suspension of a hyperbolic automorphism of a complex torus. In the second case, if the image of D is the complement of a homomorphism of the graph of homeomorphism of P1 of C, then we prove that the holonomy homomorphism is injective. And since because of that form, the map U conjugates H1 and H2, so well, we prove that H1 is injective, and then that the image of H and that of H1 is discrete. So we are starting to get a discrete subgroup of PSL2. So this is how we get the geodesic flow. We also prove that the image of H1 is co-compact. And and in fact, we can assume that U is in fact equaling the identity. And using a finite cover, we can assume that the image of H1 is torsion free. So we get a compact hyperbolic 3 manifold. And by Heifliger, since we're going to say the PSL2 times PSL2 structures of our flow and that of a geodesic flow on a compact hyperbolic 3 manifold are almost the same by Heifliger and Barbeau. There exists a conjugation between the structures of our flow and that of the geodesic flow, and this is how we conclude to the fact that after a finite cover, our flow is orbit equivalent to the geodesic flow of a compact hyperbolic 3 manifold. Thank you for your attention and sorry for the delay.
Thank you, Mounib. So, are there any questions?